Okay, then let us start. So today what I'm going to do is introduce several models to you, right? Very commonly used, often used discrete distributions, right? These are used as models for different applications. Uh, so they are actually very useful, right? So I'm going to talk about mm, something called discrete uniform distribution, and then Bernoulli distribution, binomial distribution, Poisson, geometric, hypergeometric, negative binomial, like several models. Those are the most commonly used models for discrete distributions. So let us start with the first one, discrete uniform distribution. This is not a very commonly used one, but as a completion, I have included that. Suppose you have a random variable x, and uh, it can take several values, finite number of values, and suppose all the values have equal probability. Right. So x can take several values with equal probability. Then we say x has a discrete uniform distribution. So, for example, if x can take uh, k values, and suppose those values are x1, x2 up to xk, right? Then the probability that capital X is equal to any xi, x equal to x1, x equal to x2, x equal to x3 will be 1 over k, right? So, if that is the case, then we say x has a discrete uniform distribution. To take a simple example, if you roll a die, right, say x is the value that you get, right, the face uh, number when you roll it, you get a face on the upper face, and then the number can be 1, 2, 3, 4, 5, 6. So finite number of numbers. Each number has equal probability. Right? So if you say probability x equal to 1 is equal to 1 over 6, probability x equal to 2 is also 1 over 6, and so on. So therefore, we can say in that case x has a discrete uniform distribution. But in particular, if, for example, if like in the previous example, sometimes the possible values can be consecutive values in a certain range from a to a plus k, for example. It doesn't have to be like that. In general, it can be a random variable can take several values x1 up to xk. They don't have to be consecutive values. But in particular cases, if they are consecutive values between some a and b, for example, some two values a and b, then also we can say if the numbers are equally likely, then we can say random variable has a discrete uniform distribution. In that case, we can obtain an expression for the expected value of x and the variance of x, right? If the possible values are consecutive values between a and b, then we can easily derive expression for expected value of x and the variance of x. I am not going to derive them here because I have already given you the definition. So I leave the derivations for you to do, because these are just mathematics. We know the expected value is equal to expected value of x is equal to the summation over all possible x's, x times pxx. Right. And the variance usually we calculate by using the computational formula that is usually obtained as expected value of x square minus expected value of x whole thing square. Right. So in order to get the variance of x, you need the expected value of x square. Expected value of x square will be summation over all possible x's, x square times pxx. Right. So you need to get this one and these two to get the variance. So you can just substitute the expressions and then simplify using mathematics and get these expressions very easily, right? So if the possible values are consecutive values between a and b, then of course the expected value will be a plus b divided by 2. And then using this method, you can show that the variance will be uh, equal to b minus a plus square minus 1 divided by 12. Right. So you don't have to remember anything these things, but just you have to know what they are, right? So this is, as I mentioned, it's not a very commonly used model because there are very little situations, limited number of situations where the possible values are equally likely. But the next few distributions will be very useful. I have just included this one for the completion, right? Uh, so the next one, Bernoulli distribution. Actually, Bernoulli distribution is also not directly used as a model, but it is used as a building block for several other distributions. So in order to talk about Bernoulli distribution, we need first of all another word called Bernoulli trial. Bernoulli trial. The Bernoulli trial is an experiment where the outcome can be one of the two categories, right? There are, if the outcome of an experiment has only two possibilities, then we call that experiment a Bernoulli trial, right? So, for example, if you toss a coin, then there are two possibilities, head or tail. So, tossing a coin is a Bernoulli trial. If you, for example, roll a die and observe whether the number is even or odd, right? So in that case, the experiment is a Bernoulli trial. You are observing whether it is even or odd, right? There are only two possibilities. If you observe some product and categorize it as a defective one or non-defective one, in that case, you have a Bernoulli trial. Right? Or if you look at the result of a student and then categorize it as pass or fail, that is a Bernoulli trial. Right? So like that, in general, we call them success and failure. Two possibilities are usually called success and failure, but they are not virtually successes or failures, but according to the problem, we take one category as a success and the other one as a failure. Right. So usually we will denote success by simple S and failure by F. Right. So the random variable here, the random variable by definition has to be a number, real number. So in this case, for example, if the outcome is a success, we define X to be 1. Right. If the outcome is a success, then X, the random variable X will be equal to 1. Otherwise, if the outcome is a failure, then we take X to be 0. So therefore, when we talk about a random variable related to a Bernoulli trial, the random variable takes only two values, 1 and 0. 1 and 0. So suppose, for example, in general, probability of a success in any trial is some value theta. Right? Not always they are fair coins or anything, but sometimes the probability of success can be some value and the value will be 1 minus that value. So generally, therefore, we denote the probability of a success by theta. So if you denote it like that, then we can say probability capital X is equal to 1, because 1 when X equal to 1, if the result is a success, so the probability X equal to 1 is theta. Right? Then probability X equal to 0 will be 1 minus theta. So in that case, we say X has a Bernoulli distribution. The random variable X has a Bernoulli distribution with parameter theta, where theta is the probability of a success. So that is the notation. That's how we usually denote, right, when a random variable has a Bernoulli distribution. So we can write down the probability. We have already looked at it in a previous example, this one. We can write down the probability mass function when X has a Bernoulli theta distribution, either like this or like this. Generally, we write it like this. So you can see, for example, the probability Px1, that is the probability capital X equal to 1, will be given by when you put simple x equal to 1, that is theta to the power 1 minus 1 minus theta to the power 0. So that is theta. Px0 means probability capital X equal to 0. So that is given by obtained by putting simple x equal to 0. So you have theta to the power 0, 1 minus theta to the power 1, that is 1 minus theta. So both probabilities can be obtained from one formula here, right? We can show that if the mass function is like this, that is if the random variable has a uh, Bernoulli theta distribution, then the expected value will be equal to theta, right? This is a very simple one. I am asking you to now derive that. Find out the expected value of x using that definition there, right? In this case, x can take only two values, right? The probability x equal to 1 is theta, probability x equal to 0 is 1 minus theta. So how do you get expected value of x? Expected value of x will be equal to 1 times the probability x equal to 1 plus the 0 times the probability x equal to 0, right? So 1 times probability x equal to 1 is theta. So 1 times theta plus 0 times whatever, that part will not come. So therefore the answer will be theta. And then we can show that if x has a Bernoulli theta distribution, then the variance will be equal to theta times 1 minus theta. So how do we derive that? In order to derive that, actually it's easy if you use this formula here. So for that we need expected value of x square. So what will be the expected value of x square in that case? Expected value of x square will be 1 square, right? X square. When x equal to 1, you have x square and then px1 plus 0 square px0. So this is 1 times px1, that is the same as the probability capital X equal to 1. So that is theta plus 0. So that is again theta. Expected value of x square is also theta. So therefore the variance is equal to, can obtain from this formula here. So the variance of x, sometimes I write down V only, sometimes I write down VAR. I will just write down variance of x. Expected value of x square minus expected value of x whole thing square. So that is theta minus theta square, that is equal to theta times 1 minus theta. Right. So therefore, if x has a Bernoulli theta distribution, then variance of x is equal to theta times 1 minus theta. The mean is equal to theta. Right. So I have also added at the same time the required the R commands that you can use to get the density function or the mass function in this particular case, and then to calculate probabilities, quantiles, and a random number generation. Of course, these are not very useful for the Bernoulli distribution. You only very rarely calculate these ones. But anyway, there is no particular distribution for the Bernoulli. We have to use the binomial distribution in this case. Bernoulli distribution is actually a special case of the binomial distribution. R has a series of functions for probability, CDF, and density function for the binomial distribution. So we can actually, if we want, we can use the same function to get the corresponding values for the Bernoulli distribution. Right. So therefore, I will when I come to the binomial, I will show you that, and then I will come back if necessary for the Bernoulli, right? Because Bernoulli is a special case of a binomial distribution. Now, on the other way around, actually binomial is again a special case of Bernoulli also. So both ways you can consider, right? So that's the building block actually. If you are doing some experiment where the outcome is generally a success or a failure. Now suppose you are doing this experiment, a Bernoulli experiment, a fixed number of times. where the number of times is fixed and we know that, a known value. In general, suppose we are doing this Bernoulli experiment n times, where n is known. Right. So each time we get a success or a failure. Each time we get a success or failure. Uh, and there are some other assumptions that we have to, something called binomial conditions, for us to be able to talk about this binomial distribution. Right. So the first requirement is this experiment. We have to have a sequence of fixed number of Bernoulli trials, n number of Bernoulli trials, where the n is fixed in advance. The second requirement is that the outcome in one experiment, whether you get a success or failure in one experiment, should not depend on whether you got a success or failure in other experiments. So the outcomes should be independent. The third requirement is the probability of a success should be the same in each trial. For example, if you have probability of success theta in the first trial, in the second trial also you should be able to assume that the probability of success again theta. In the third one also, probability of success should be theta. It should not change with the experiment. So if you can assume these three conditions, and if you define the random variable x to be the number of successes, the total number of successes in this n experiments, that is the random variable x. Then we say x has some distribution, where the name of that distribution is the binomial distribution. We say x has a binomial distribution, right? So there are n number of Bernoulli trials, right, where we assume that the outcomes are independent and the probability of a success is the same for each trial. Then we define the number of successes in n trials to be the random variable. In that case, the distribution of x is called the binomial distribution. Right. Okay. So in that case, this is how we denote x has a binomial, means binomial, and then we have to specify the two numbers here. Otherwise, we cannot calculate anything. We have to know the value n, and you have to somehow specify the probability theta. That is the probability of a success in any trial. Right. So we can show that in that case the probability mass function is given by this formula. Right. Actually, deriving these are not that necessary, but let's anyway, because this is a mathematics class also. Let's try to derive this equation. We have already actually done that in last week, but that was for a particular case. Let us now look at this one in general. So what we are looking at is we are doing n experiments. In each case, result is a success or a failure. We are looking at Pxx. So that means the probability that x is equal to simple x. So in order to derive that, let us look at some special cases of simple x. Right, instead of going directly to a common number, let us look at several cases. Then you will be able to get the expression by looking at the pattern. Right. So you have n trials. The probability of a success is the same in each trial. So what is the probability? What are the possible values of x in this case? What are the possible values of x? Capital X. X is the number of successes. Suppose, for example, n is equal to 10. We are doing it 10 times. So what are the possible values of x? X can take 0, 1, 2, up to 10. So in general, therefore, x can be 0 up to n. If you are doing it up n times, then the possible values are from 0 to n full numbers. So let's therefore, we should be able to talk about Pxx. Right. Pxx. So we should be able to calculate Px0, Px1, Px2, and so on, Pxn. Right. These are the things that we are interested in. If we can get all these things in one formula, that's fine. So let's look at Px1, Px0. That is the same as probability x equal to 0. How can that, what is that probability? X equal to 0 means no successes in n trials. That means all of them are failures. Right. So what is the probability that all of them are failures if one probability of one failure is theta? All of them are failures means first one is a failure and second one is a failure and third one is a failure until nth one is a failure. So we have the probability of several intersections. First one is a failure is one event, second one is a failure is another event, third one is a failure is another event, and so on. So you can consider it as we are looking at the probability of intersection of several events where the events are independent, because the outcome in any trial is independent of the outcomes of the other trials, right? So therefore, the probability of the intersection will be equal to the product of the probabilities by the multiplication rule. So therefore, this will be probability that the first one is a failure is 1 minus theta, right? Times again, second one is a failure 1 minus theta, like that. 1 minus theta to the power, there will be n times of this. So that is therefore 1 minus theta to the power n, right? So let's look at Px1. That is the probability x equal to 1. What is the probability of getting one success in n trials? What are the possible ways of happening that? Yeah, all the others. Yeah, first one is a success and all the others are failures. Or second one is a success and all the others are failures. Or third one is a success and all the others are failures, and so on. Right. So when you say those O's are mutually exclusive, therefore there will be some additions of probabilities within each O event. Then again you have first one is uh, success and all others are failure. Second one is a failure and third one is a failure and fourth one is a failure up to nth one is a failure. Right. If the second one is the success, then first one is a failure and second one is a success and third one is a failure, and so on. So therefore, this probability will be equal to, so in within any one possibility, there is a one success and n minus one failures. So therefore, for one possibility, there will be theta to the power 1 minus theta to the power n minus 1. How many of them are there? How many possibilities are like that? N possibilities. So that's then probability x equal to 1 px1 n times theta to the power 1 minus theta to the power n minus 1. Then px2, that is probability x equal to 2. Right. How many possibilities are there? How many ways that can happen? Right. There should be two successes in n places, right? So if you put, for example, if you are having filling some n boxes, you have to put two successes to two boxes, two of those boxes, and the other ones will be automatically failures. So how many ways can you select those two boxes out of n boxes? NC two ways, right? NC two ways you can select, right? So therefore, this event can happen NC two ways, number of ways. In each way, what is the probability? There will be two successes within connected by ands. So theta to the power 2, 1 minus theta to the power n minus 2. So therefore, this will be equal to NC2 theta to the power 2, 1 minus theta n minus 2. Right. Now you can write down a general formula. Right. What will be Pxx? That is probability x equal to simple x, where simple x can be 0 or 1 or 2 or 3 or like that up to simple n. What will be that general formula? You can get derived from this one, right? So therefore, so in this case, we need X number of successes out of N trials. It's like filling X boxes, X number of boxes out of N boxes with successes, and the other ones are failures. So there are NCX ways of choosing those X boxes to put successes, and then the probability of any of those will be theta to the power X times 1 minus theta to the power N minus X. So this is NCX theta to the power X 1 minus theta to the power N minus X, where this X can be 0, 1, 2 up to N. So that is what you have here. That is the probability mass function of a binomial random variable with N and theta. Probability mass. Right. So you can use this model, this as a model for a lot of situations, right? One situation is, for example, very simple situation. Suppose you are tossing a coin 10 times, right? And I ask, what is the probability of getting three heads? Right. So I'm asking, what is the probability that x is equal to 3, where in this case x will have x is the number of heads in 10 tosses. X is the number of heads, right? So I'm asking, what is the probability x is equal to 3? That is, if you know the value of theta, then for example, if you take theta to be half, then you can just put the number NC3 half to the power 3, 1 minus half to the power 10 minus 3. So that will give you the probability, right? And similarly, what is the probability of getting less than 3 heads in 10 tosses? So in that case, you are asking, what is the probability? Probability x less than 3. Right. So x can take, if you are tossing it 10 times, x can take 0, 1 up to 10. So in this case, this is the probability x equal to 0 plus probability x equal to 1 plus probability x equal to 2. So they are the same as px0 plus px1 plus px2, and each of these you can obtain from this formula and then substitute. Actually, now we are not going to do anything manually. We will, if you got, we will be using R to calculate probability. So if I want to get this probability using R, what command should I use? The command, the commands are, what are the commands? For the binomial, D binom, that gives you the mass function, right? D binom gives you the mass function. P binom gives you the cumulative probability, right? D binom and P binom. P binom will give you the cumulative probability. Q binom gives you quantiles, and R binom gives you random numbers, right? So shall we start R and then do at the same time? So start your R. We will look at some examples. First, I will just do mathematical calculations, and then we will come to some, at the end, I will come to some practical problems, because if I do the practical problems here at the end of the each distribution, you know which model to use in that particular case. That is not what I want. I want you to read the question and then choose a suitable model out of the models that you have learned at the end. Right? එහෙම නැතුව එක එක මොඩල් එක යටතේ ගන්න හදපුවම ඒ මොඩල් එකෙන් තමයි එන්නේ කියලා ඔයගොල්ලෝ දන්නවා. එතකොට ඒක දැනුමක් නෙමෙයි. right? අවශ්‍ය වෙන්නේ ගැටලුවක් විසඳුනට පස්සේ Tamanට මොඩල්ස් කීපයක් තියෙනවා. ඒකෙන් සුසු මොඩල් එක තෝරගෙන ඉවරලා හදන්න පුළුවන් වෙන්න ඕනේ. ඒ නිසා මම එතෙන්ට එන්නම් පස්සේ. But anyway, generally suppose, for example, suppose x has a binomial, say 20 and 0.8. That means we are looking at the number of successes in 20 Bernoulli trials, where the probability of a success in any trial is 0.8. Right? So let's calculate using R the probability x equal to 5. Probability x less than or equal to 8. Probability x less than 3. probability x greater than or equal to 2, right? 5. Probability x greater than 5, probability x between 2 and 7, greater than 2 and less than or equal to 7. Let's calculate these things using R. Right. So the functions are d binom, and then the arguments are, personal argument is the value, for example, 5 here, simple x, and then you have to give the value n and the value theta. So those are the order, natural order of the arguments, d binom, and the other one is p binom. So you calculate a p binom again at some x value and n and theta, right? Those are the two functions required for this. Right? So what is the function that you use for this one? This is the mass function at given point, right? So therefore you use d binom, right, at value 5. So this is actually d binom 5 and n is equal to 20, theta is equal to 0.8. So if you type this one and run it, you will get the value d binom. Right. That is the same as putting n equal to 20 here and x equal to 5 here, theta equal to 0.8 in this formula. Right. You get that value. For this one, what function you use? You have to use p binom because it's less than or equal to, greater than or equal to. In that case, we can use. But anyway, p binom gives you less than or equal to cumulative probability, right? It gives you f, capital F x x. That is by definition, that is the probability x less than or equal to simple x. Remember, I told you that equal sign is important here. Right? Cumulative distribution is defined as probability x less than or equal to simple x, and this one gives you this. Right. So here we need probability x less than or equal to 8. So this is actually f x 8 according to that definition. So you should use p binom. Actually, these are simple letters. P binom 8 and 20 and 0.8. So that will automatically add 9 probabilities because probability x less than or equal to 8 means probability x equal to 0 plus probability x equal to 1 plus probability x equal to 2 up to probability x equal to 8. Right. So if you are doing it manually, you will have to add 8 probabilities. Each one you have to obtain from this formula. Now, just one command. That command will give you that probability. Right. How do you answer this one? Probability x less than 3. How would you do that using R? Less than 3. This one I could get directly using p binom because it is actually the cumulative, because less than or equal to sign is there. But here only less than, right? So what I can do is actually I can write down this one with the equal sign here and then use this function, right? So if you write down with the equal sign, this is equal to the probability x less than 3 means 0 or 1 or 2, right? So less than or equal to 2, right? So this is actually therefore fx2, and therefore this is the p binom 2 comma 8 comma 20 comma 0.8, 20 comma 0.8. Right. So how can you find out this one then using R? These are the two functions you can use, right? You can write down that one as, this one as 1 minus probability x less than or equal to 1, right? Greater than or equal to 2. The other two are 0 and 1. So that is less than or equal to 1. So that is actually, this is the complement of this event. So therefore the probability is 1 minus. So this is equal to 1 minus fx1. 1 minus fx1. So you can say in R, you can say 1 minus p binom 120.8. 1 minus p binom, you can say like that. There is another way of doing it, because in R it gives automatically it gives you less than or equal to probability. That is the default one. But in all of these functions, there is another argument called uh, I don't remember. I have to check. If you want, you can get the right tail probabilities also. But by default, it gives you left tail probabilities. Let's get the help, because I don't remember the last. මේ shift එක වැඩ කරන්නේ නැහැ වගේ. මේකේ press. shift අන්ත තව එකක් තියෙනවද shift? right. Binom. So these are the ones that we were using x, and then size is n, then the probability of success theta, and there's another one called lower tail. Lower tail is the next one. So naturally it says lower tail is equal to true, so that is the default. If you say lower tail is equal to false, it will give you the right tail probability, right side probability. Right. So that will give you, if you say p binom and then 120.8, and then you have to say right lower tail equal to false, then it will give you the probability x greater than or equal to 1. But it's always, for me, it's easy to remember one than remembering other ones, because it goes with the cumulative distribution function definition. P binom gives you the cumulative distribution, so that's easy to remember. So therefore, I usually use that one always, just to take 1 minus or not. You have to decide. Right. So then, so that's how you get it. How do you get this one? Probability x greater than 5. You can write down this one as 1 minus probability x less than or equal to 5. Here x greater than 5 means 6, 7, 8, 9 up to 20. So 1 minus the complement of that. So therefore this is equal to 1 minus p binom 5, 20.8. P binom 5, 20.8. So always remember to work with the equal sign, the cumulative probability. Okay, the last one. Okay, I will leave that for you to do. Do it. Probability x, between x greater than 7 but less than or equal to, greater than 2, less than or equal to 7. How do you find out that? Can write down this one as probability x less than or equal to 7 minus probability x less than or equal to 2. Right? X less than or equal to 7 කිව්වම බිංදුව සිට 7 දක්වා සියලුම probabilities වල එකතුව less than or equal to 2 කිව්වම බිංදුව සිට 2 දක්වා probabilities වල එකතුව. එතකොට ඒක අඩු කරපුවාම 2කට වඩා වැඩි 4ට වඩා අඩු probabilities ටික එනවා. So this is p binom 720.8 minus p binom 220.8. Right. So that's how you can calculate the probabilities. Using D binom, you can get directly the mass function at a given value. Using P binom, you can get any other probability. Now, let us just check the meaning of the expected value. We know that if x has a binomial, say, n theta distribution, then we just few minutes ago we learned that expected value of x is equal to n times theta and variance of x is equal to no, I didn't actually get that equation. In the note you have that n times theta and then n times theta times 1 minus theta. That will be the expressions. Now, can you see here some kind of relationship between this and the previous one? Bernoulli and binomial. Expected value and the variance. Look at the formula given for the expected value of the Bernoulli and expected value for the binomial. Expected variance for the Bernoulli and variance for the binomial. Right. Now, this is n times the Bernoulli expectation. This is the n times the Bernoulli variance. Why is that? In the Bernoulli case, we define x to be 0 or 1, right? X equal to 0 if you get a success in a single trial. Otherwise, if you get a failure in that trial, you get 0, otherwise 1, right? If you get a success, you get 1, right? Now, let me define x1 to be 1 or 0. 1 if you get a success, 0 otherwise in the first trial. Now, let's look at the second trial and define based on the second trial again 1 or 0. If the second trial gives you a success, x2 will be equal to 1, otherwise 0. Like that, let me define x3 up to xn. Each x1 up to xn is a 0 or 1, right? Now, let us look at, so what is the distribution of x1? x1, suppose the probability of a success is theta. So, x1 will have Bernoulli theta distribution. x2 will have again Bernoulli theta distribution, like that. Up to xn also will have Bernoulli theta distribution. These all are independent. Right. Independent random variables. Right. So we can say x1 up to xn are IID, independent and identically distributed. x1 up to xn are IID random variables here. Right. So now let us look at a new random variable. Let's say y is equal to x1 plus x2 plus x3 plus xn. If y is equal to x1 plus up to x2 up to xn, then what does y give you? x1 is equal to 1 if you get a success in the first trial, otherwise it is 0. x2 is 1 if you get a success in the second trial, otherwise it is 0, like that. So if you add all those ones, what will you get? Can you give a meaning to that quantity y? The sum will be 1 or 0, 1 or 0, 1 or 0, right? Sum of those. So sum will be equal to what? Sum of x1 up to xn will be the sum of ones. Sum of ones, right? Sum of ones means sum of successes in n trials. So y actually is the number of successes in n trials. So according to what we learn here, what should be the distribution of y? Y should have a binomial distribution. Y should have a binomial distribution. So now we can see that binomial distribution is actually the sum of independent and identically distributed by Bernoulli random variables. Right? You can consider binomial distribution as the sum of IID Bernoulli random variables. That is another way to look at binomial distribution. Sum of IID Bernoulli. Right. So therefore, variance of expected value of y should be expected value of all of this. So that is equal to expected value of x1 plus expected value of x2 up to expected value of xn. That is coming from the properties of the expected value. Expected value of y should be equal to sum of the expected values of x1 up to xn, and we know from the previous Bernoulli distribution, this is theta, this is theta, this is theta. So therefore, theta plus up to theta n times. So that is why you get expected value of y to be n times theta. Right. Expected value of y is n times theta. That is, if y has a binomial distribution with n and theta, then expected value of y is equal to n times theta. Right. What is the variance of y? Variance of y is equal to variance of x1 plus x2 plus up to xn. Because x1 up to xn are independent, this is equal to variance of x1 plus variance of x2 plus up to variance of xn. That is, you can get the variance of a sum as the sum of the variances when the random variables are independent. Now we know from the Bernoulli distribution, each of these is equal to theta times 1 minus theta. You have n of those. So therefore, this is n times theta times 1 minus theta. That is why the variance of a binomial distribution is equal to n times theta times 1 minus theta. Right. So binomial distribution can be viewed as generally as the number of successes in n Bernoulli trials. That is one way to look at it. The random variable is the number of successes in n Bernoulli trials. Or it can be viewed as sum of independent and identically distributed Bernoulli theta random variables. Right. Both ways you can express the binomial distribution. Right. Okay, here is a very simple example. Let's look at that. Let's get the values. If n independent components are inspected and each component has probability 0.03 of being defective, then the number of components among the 10 follow a binomial distribution with parameters n equal to 10 and theta equal. So this kind of a situation occurs. Now, one example is if you are doing some experiment fixed number of times, and each time if you can classify the outcome as one of the two categories, generally success and failure, Then if you are interested in the number of successes in the n trials, then you are using the binomial model for x. That is one practical application. Another application is like this. If you are looking at a large population, very large population, and if you are taking a random sample of say n items, where each item can be success or failure, or in general defective or non-defective, and if you are interested in the number of defectives in the sample, right, in that case also you can use the binomial distribution as the distribution of x. Right. Why do we use that binomial distribution in that case? Remember, we need three conditions. Right. In the previous example, where we are doing the experiment n times exactly, and then each time outcome is a success or failure, and if the probability of a success is the same, ideally then the number of successes in n trials will have a binomial distribution. This situation is a kind of approximation for the binomial distribution. This is when you are sampling from a finite population without replacement, but if the population is very large, right? අපි හිතමු population එක තියෙන දසලක්ෂයක් තියෙනවා කියලා items මොකක් හරි container එක. So you are taking 50 items out of that. Right? You are taking without replacement. දාලා ආපහු ගන්නෙ නෑනේ අරන් බලන්නේ නෑ මොකද defective ද නැද්ද කියලා 50ක් අරන් ඒ 50 ඇතුලේ තියෙන defective ගාන බලන්න. So if you define x to be the number of defective items in this 50 sample of 50 items, can we use the binomial distribution as the distribution of x? Right? X can take values from 0 to 50. Right? Every time we can, for example, if you are interested in the number of defectives, so each item is defective or non-defective, success or failure. Right? Next one, whether one is defective or not is independent of whether the other one is defective or not. Can we assume that condition to be true in this case? Actually, no. In this case, the outcomes are not independent. Like theoretically, they are not independent. අපි හිතමු 10000ක් තිබුණා කියලා ඒකෙන් අපි 50ක් තිබුණා 100ක් තිබුණා ඩිෆෙක්ටිව්ස් කියලා හිතන්න ඔක්කොම ටික. දැන් පළවෙනි එක ඩිෆෙක්ටිව් ගත්තට පස්සේ පළවෙනි එක ඩිෆෙක්ටිව් කියලා අපි දන්නවා නම් දෙවෙනි එක ඩිෆෙක්ටිව් වීමේ සම්භාවිතය කොච්චරද? 10000ක් තිබුණා ඒකෙන් 100ක් ඩිෆෙක්ටිව්. ඒතකොට 9900ක් තියෙනවා non ඩිෆෙක්ටිව්. අපි හිතමු අපි ඉස්සරලාම හොයනවා දෙවෙනි එක පළවෙනි එක ගැන කියන්නේ නැතුව මම අහනවා දෙවෙනි එක ඩිෆෙක්ටිව් වීමේ සම්භාවිතය මොකක්ද? ඒක ඔයගොල්ලන්ට හොයන්න පුළුවන් total probability law පාවිච්චි කරලා. right පළවෙනි එක ඩිෆෙක්ටිව් වෙලා දෙවෙනි එක ඩිෆෙක්ටිව් වෙන්නත් පුළුවන්. පළවෙනි එක non defective වෙලා දෙවෙනි එක defective වෙන්නත් පුළුවන්. ඔය දෙකනේ වෙන්න පුළුවන්. ඒතර මේ දෙක පාවිච්චි කරලා total probability law දාලා දෙවෙනි එක defective වීමේ සම්භාවිතය හොයන්න පුළුවන්. ඊට පස්සේ ඕනනම් මම අහනවා පළවෙනි එක defective නම් මම ඒක බව දන්නවා නම් දෙවෙනි එක defective වීමේ සම්භාවිතය මොකක්ද? එතන අහන්නේ මොකද්ද? ඒතර conditional probability that the second one is defective given that the first one is defective. ඔය දෙක හෙව්වොත් එහෙම ඔයගලට පේනවා ඔය දෙක උත්තර දෙක සමාන නැහැ. ඔය උත්තර දෙක සමාන නැහැ. ඒ කියන්නේ දෙවෙනි එක ඩිෆෙක්ටිව් වීමේ සම්භාවිතාවය පළවෙනි එක ඩිෆෙක්ටිව් වෙද නැද්ද කියන එක මත රඳා පවතිනවා. අපි ෆයිනයිට් පොපියුලේෂන් එකකින් ගන්න. ඔයලා බලන්න. දැන් වෙන හැටි දන්නවනේ. ඒතර ඔය දෙක සමාන නැහැ කියලා කියන්නේ මොකද්ද? අර outcomes are not independent. Not independent. සමාන නැති වුණාට හැබැයි ওই probabilities දෙක ඉතාම ආසන්න වශයෙන් සමානයි. මොකද population එක 10000 right 10000 වලින් ගිහිල්ලා හිටන් ඊට පස්සේ දෙවෙනි එකේ 9999 වලින් එන්නේ. right එතකොට පෙර දෙකම සමාන තමයි බොහෝ දුරට සමානයි. නමුත් theoretically exactly සමාන නැහැ. right එතකොට ඒ නිසා theoretically නම් outcomes are not independent. But usually we can use the binomial model to find out to talk about the probability of regarding the number of failures, number of defectives in the sample. In this case also we usually use the binomial model. So ඒක නිකන් approximation එකක් විදියටයි පාවිච්චි කරන්නේ. exact model එකක් නෙමෙයි. මොකද probability හොයපුවාම එන උත්තරවල වෙනස ඉතාම negligible if the population size is very large. Right? So therefore, that is the second example, second application of binomial model. You can use the binomial model as the number of successes in a sample of n items taken without replacement from a large population. If you are taking a very large population and if you are interested in the number of successes in the sample, right? Generally, samples are smaller relative to the population. So, in that case, the number of successes or number of defectives in the sample doesn't exactly have a binomial distribution, but approximately it has a binomial distribution. Approximation comes because of the independence assumption is not exactly satisfied. බයිනෝම එහෙම වුණාට අපි බයිනෝමියල් මොඩල් එක තමයි එතනදී පාවිච්චි කරන්නේ. බොහෝ දුරට probability සමාන වෙනවා exact තත්ත්වේ නැතත්. ඒතර ඒක තමයි දෙවෙනි application එක. ඒ වගේ එකක් තමයි මෙතන තියෙන්නේ. If n independent components are inspected, components independent වුණාට events independent වෙන්නේ නැහැ. ඒ events ගැන අපි බලනවා. result එක out failure ද නැත්නම් success කියන events are independent කියන එක තමයි condition එක. Right? එතකොට inspected each other has probability 0.03 of being defective. ඒක කොහොමද දන්නේ? මේක අපි සාමාන්‍යයෙන් population එකක තියෙන එක දන්නේ නැහැ. population එකක තියෙන defective proportion එක අපි සාමාන්‍යයෙන් දන්නේ නැහැ. ඒතර ඔය ගාන ආවේ කොහෙන්ද? ඒක ඇවිල්ලා estimate එක. using some other previous known estimate, right? යම්කිසි sample එකක් කලින් අරගෙන population එකෙන් මේ production එකෙන් අරන් හොයාගෙන තියෙනවා. ඒකේ සාමාන්‍ය මේ production process එකේ 103ක් defectives හැදෙනවා කියලා හොයාගෙන තියෙනවා. ඒතර ඒක තමයි මෙතනදී theta විදියට පාවිච්චි කරන්නේ. Right? In general, if the production process produces 3% defective products, we take that as the probability that any item being defective. So we have to know that value to calculate any probability. එහෙම නැත්නම් we can get only an expression in terms of theta. If you want to calculate the probability, you have to know the value. In that case, you have to estimate and use that estimate as the actual value to get some value, probability, right? So දැන් මෙතන අහන උදාහරණයක් විදියට මෙතන මම දීලා තියෙන condition මේ commands ටික තමයි දීලා තියෙන්නේ. ඒතර ඔක කෙනෙකුට අහන්න පුළුවන් what is the probability there will be less than 2 defectives, right? More than 5 defectives, 0 defectives, 1 defective, whatever. You can find out probabilities. These are going to be useful in practical applications. We will see some applications little later, right? Huh? Full screen එක නැතුව ගියකෝ මොකක් කියලා? Zoom එකෙන්ද? නෑ. මේක ආවේ නෑ. present කියන්නේ. ඒත් නෑ. මොකක්ද? full screen කියලාත් එන්නේ ඒකමද? දැන් ඉස්සෙල්ලා full screen තිබුණානේ. කොහොමද ඒක නැතුව ගියේ? exit full screen, press escape. exit වෙන්න නේ කියන්නේ දැන්. zoom ද? මේකෙන්ද? ඒකෙන් එනවා. හැබැයි එතකොට මේ present එක නෙමෙයි එන්නේ. මේක එබුවට page එකක් යන්නේ නැහැ. line එකෙන් line එකට යන්නේ. ඉස්සෙල්ලා කරේ present එකෙන් තමයි. හැබැයි ඒක Domagam. Right. So binomial distribution for the moment, that is enough. Let's look at the next model, hypergeometric distribution. Hypergeometric. So as I mentioned, we can use the binomial model when you are taking a sample from a finite population, and if you are interested in the number of successes in general in the sample. You can use the binomial model if the population size is very large එතකොට ඒ වෙලාවේදී අපිට මේ we can use binomial distribution as an approximate model. යම්කිසි විදියකින් population එක finite වුණත් right අපි sample එක ගන්න with replacement නම් if you are taking a sample with replacement and categorize each item as a defective or non-defective, in that case the number of defectives in the sample is exactly binomial with replacement ගන්නවා. ඒතකොට population එක වෙනස් වෙන්නේ නැහැ නේ. ඒතකොට probability අර conditional probability එකයි unconditional probability එකයි දෙකම සමානයි. ඒතකොට independence එතනදී තියෙනවා. Right. If you are taking a sample, even if the population is small, if you are taking a sample with replacement, then the number of successes in the sample will have exactly a binomial distribution. So, but if otherwise, if you are taking without replacement, and if the population is large, still you can use binomial distribution as a model, approximate in that case. Now, another case is remaining. What happens if you take a random sample from a finite population without replacement, and if the population is not that large? Population එකකින් අපි sample එකක් ගන්නවා. ඒ population එක එච්චර ලොකුත් නෑ. අපි ගන්නේ සාමාන්‍ය විදියට without replacement. සාමාන්‍ය sample එකක් ගන්නවා කියපුවම මේකෙන් අදහස් කරන්නේ without replacement, unless otherwise specifically mentioned that the sample is with replacement. So මේ වගේ අවස්ථා එනවා. We have to take a sample from a certain finite population without replacement, and we are interested in the number of successes in the sample. Right. So let's look at that case. Suppose that the population of size k contains m items of a certain kind. Right. With population එකේ තියෙන හැම item එකම අපිට වර්ග දෙකකට බෙදන්න පුළුවන්. Success or failure. හැම item. Each item can be categorized as a success or failure. Suppose in the population there are altogether k items, and out of them m items are successes. Right? Like gender, males and females, or sometimes like some other defective or non-defective, but for population can be small, like that. A sample of n items is taken from this population without replacement, and we are interested in the number of successes in the sample. So what will be the distribution of x in this case? What are the possible values of x? What is the distribution of x? What is the mass function, and so on? That is the question. So we have a situation like this. We have a population with k items. There are successes and failures. Right? Suppose there are m successes and k minus m failures. We are taking a sample of n items, and there will be some successes and failures, right? Successes and failures, right? So let us denote the number of successes in the sample by x, right? So that is the variable. Suppose x is the number of successes in the sample. Suppose that is, we are interested in what is the probability x equal to simple x. That is the question. Right? We are interested in pxx. Right? So capital X denotes the number of successes in the sample. So if there are x number of successes, then there should be n minus x failures. So the question is, what is the probability capital X equal to simple x? In other words, what is the probability of getting this kind of sample? What is the probability of getting that kind of sample? We have looked at this kind of example previously. So now we need a general formula for that. How do we get that? I did it in two ways in the last class. One method was I wrote down the full sample space. Right? It's like මම හිතන්නේ මම බැලුවේ red balls and black balls or ball වර්ග දෙකක් නේ. හැම ball එකම B1 B2 B3 කියලා දැම්මා. ඊට පස්සේ red white and white 1 white 2 white 3 කියලා දාලා වෙන වෙනම හැම බෝලෙම වෙන් කරනවා කියලා හිතාගෙන sample space එක ලිව්වොත් එහෙම we get equally likely sample space. Outcomes are equally. ඒ ආශ්‍රයෙන් මම probability mass function එක derive කරා ඒ විදිහට. එහෙම නැත්නම් අපිට පුළුවන් මේ probability mass function එක conditional probability පාවිච්චි කරලා හොයාගන්න. ඒත් ඒක ගිහිල්ලා බලන්න ආපහු. දැන් අපි ආයසරයක් බලමු කොහොමද මේක ගන්නෙ කියලා. දැන් classical method එක පාවිච්චි කරොත් equally likely outcomes විදියට ලිව්වොත් එහෙම මෙතන තියෙනවා ඔක්කොම k items. right. So අපි දැන් තියෙන අපි හිතමු successes ටික S1 S2 S3 S1 up to SM කියලා define කරනවා. ඊට පස්සේ failures ටික F1 F2 F3 up to F k minus m කියලා define කරොත් අපි denote කරොත් උදාහරණයක් විදිහට ඔක්කොම තියෙනවා එකිනෙකට වෙනස් k items ටිකක් තියෙනවා. දැන් ඕකෙන් මම sample එකක් ගන්නවා size එක simple n වෙච්ච. ඒතර අහන්නේ ඒතර අර ඒ විදිහට ලියපු sample space එකේ n items තියෙන විදිහට ගත්ත n tuple එකක් ඒ විදිහට තියෙන ඒවා කොච්චරක් තියෙනවද ඔක්කොම අපි order එක වැදගත් කියලා හිතුවොත් if we consider the order is important how many n tuples are there out of k p kpn right k වලින් n ගාණක් තෝරාගෙන arrange කරන්න පුළුවන් ආකාර permutations kpn ප්‍රමාණයක් තියෙනවා right එහෙම නැත්නම් ඒක සමානයි kcn වැඩි කිරීම factorial n kcn වැඩි කිරීම factorial n kcn කියන්නේ තෝරාගත හැකි ආකාර ගාන ඕනම එකක් තෝරාගත්තට පස්සේ ඒක factorial n ප්‍රමාණ ආකාර ගානට arrange කරන්න පුළුවන් ඒකට ඒකෙන් වැඩි වෙන්නේ right ඒකට ඒ ගාන තමයි ඕනම sample එකක් මේ විදිහේ ඕනම sample එකක් ලැබීමේ සම්භාව්‍යය. ඒතර මේ විදිහේ particular sample එකක් මෙතන s අගයන් x ප්‍රමාණයකුයි f එවුවා තියෙනවා n-x එන්න පුළුවන් ආකාර ගන්න. අපි ඉස්සෙල්ලා ආකාර ගන්න බලලා ඉතින් ඊට පස්සේ අපිට ඕනනම් බඩි ගන්න පුළුවන් permutations වලින් arrangements බලන්න. කොහොමද ඒකෙන්? දැන් මේ x එන්න ඕනේ කොයි මොනවාගෙන්ද? මේ m වලින් එන්න ඕනේ. එහෙනම් m වලින් මෙතෙන්ට x ප්‍රමාණයක් ලැබීමේ තෝරාගත හැකි ආකාර ගන්න mcx ඊට පස්සේ මේ k m වලින් n-x ප්‍රමාණයක් තෝරා ගැනීමේ ආකාර ගන්න k m c n-x. එතකොට දැන් ඔය දෙකම වීමේ ආකාර ගන්න mcx times kcm k minus m c n-x. එතකොට මේ ආකාරයේ sample එකක් තෝරාගත හැකි ආකාර ගන්න ඒ දෙක වැඩි කරපුවාම ඉන්නේ එක ඒකේ arrangements බලන්න ඕන නම් ආයසරයක් factorial n වලින් වැඩි කරන්න ඕන. එතකොට උඩයි යටයි දෙකම factorial n වලින් වැඩි කරපුවාම කැපිලා නේද අපිට arrangements බලන්න ඕනේ නැහැ. combination බලපුවාම ඇති. එතකොට ඔයගොල්ලන්ට තේරුම් ගන්න පුළුවන් pxx එහෙම නැත්නම් probability x equal to x will be equal to what? mcx times k minus mc n-x divided by kcn. right මේ ආකාරයේ particular sample එකක් ලැබෙන්න පුළුවන් ආකාර ගන්න. අපේ event එක සිද්ධ වෙන්න පුළුවන් ආකාර ගන්න divided by the total number of samples that we can select size n. Right. So that is the probability mass function in this case and we call that the hypergeometric distribution. Hypergeometric. So in this case we say x has a hypergeometric distribution. What are the values that x can take in this case? What are the values that x can take? දැන් මෙතන තියෙන දැන් මේ sample එකේ size එක මේකට වඩා අඩු වෙන්නත් පුළුවන් වැඩි වෙන්නත් පුළුවන්. right sample size එක මේකට වඩා වැඩි වුණොත් එහෙම x කියන එක m දක්වාම යන්න පුළුවන්. sample size n කියන එක m ට වඩා අඩු වුණොත් එහෙම x කියන එක යන්න පුළුවන් n දක්වා පමණයි. right. ඒතර ඒ අනුව ගන්න පුළුවන් උපරිමාර්ගය රඳා පවතිනවා මේගේ m කියන එක n ට වඩා අඩුද වැඩිද කියන එක අනුව ඒ අනුව උපරිමාර්ගය වෙන්නේ minimum of m and n. right. x ට ගන්න පුළුවන් උපරිමාර්ගය වෙන්නේ minimum of m and n. maximum එක මේ අවමාර්ගය වෙන්නේ මෙන්න මේක කියලා ඕගොල්ලෝ පොඩක් චෙක් කරගන්න. සාමාන්‍යයෙන් බිඳුවේ සිට තමයි යන්නේ. නමුත් particular case එකක් තියෙනවා මෙන්න මේ maximum මෙතන දාලා තියෙනයි කියලා පොඩ්ඩක් කල්පනා කරලා බලන්න. සාමාන්‍යයෙන් generally යන්නේ බිඳුවේ සිට තමයි. right. So generally most of the times x can be from 0 to the minimum of these two. So this is the model that you have to use if you are interested in the number of successes in a sample taken from a finite population without replacement. Right. Number of successes in a sample of n items taken from a finite population without replacement. Right. Now let's look at again the formulas. I'm not going to derive them, but there's something that I want to explain. Let's look at the formulas for the mean and the variance. Right. We can show by definition that the mean is equal to n times m divided by k. Variance is m times m divided by k, 1 minus m divided by t, and then something here multiplied. Now again, you will see that there is some kind of relationship between these two expressions and binomial case. Right? Remember, in both cases, we are looking at the number of successes in a sample generally. Right? Binomial is used under certain conditions. Hypergeometric is used under some other conditions. But there is some kind of equivalency here. If you remember, for the binomial, expected value is equal to m times theta, where theta is the probability of a success. Probability of a success. Metandi, the probability of a success වෙන්නේ. There are k items altogether in the population. There are m successes. So what is the probability that any item is a success? M divided by k. ඉතින් මෙතනත් තියෙන එකම තමයි නේ n times theta තමයි මෙතනත් තියෙන්නේ. right. So the expected value එකේ form එක වෙනස් වෙලා නැහැ. expected value එක අතන තිබුණේ n times theta, මෙතනත් තියෙන්නේ n times theta ම තමයි. හැබැයි variance එක අරගෙදී මොකක්ද තිබුණේ n times theta times 1 minus theta. මෙතනත් තියෙන්නේ මේ වගේ එකක් n times theta times 1 minus theta. හැබැයි මෙතන තව කෑල්ලක් ඇවිල්ලා තියෙනවා. variance එක binomial එකේ variance එකම ආකාරයෙන්ම නෙමෙයි, පොඩ්ඩක් වෙනස් වෙනවා. මොකද්ද ඒ වෙනස? ඇයි වෙනස වෙලා තියෙන්නේ? මෙන්න මේකට අපි කියනවා finite population correction කියලා. finite population correction. finite population FPC. That is some correction is needed for the variance when you are getting the sample from without replacement from a finite population. Right. එතකොට මේ variance එක binomial variance එකකට වඩා අඩුද වැඩිද? එනත ආකාරයකින් මේ කැලල එකට වඩා අඩුද වැඩිද? එකට වඩා අඩුද වැඩිද? අඩුයිනේ. ඔව් එකට වඩා අඩු. එහෙනම් ඒ කියන්නේ hypergeometric වෙලාවේදී x ගේ variance එක binomial අවස්ථාවක x වල variance එකට වඩා අඩුයි. ඇයි එහෙම වෙන්නේ ප්‍රායෝගිකව? මොකද්ද එතන මොකද්ද වෙන්නේ? ඇයි variance එක අඩු වෙන්නේ? ෆෝමියුලා එකට අනුව අඩුයි කියලා පේනවා. කොහොමද එහෙම වෙන්නේ? ඈ x කියන්නේ the number of failures in the sample නේ. the number of failures අතනදී අපි ගත්තොත් මේ ඉතා විශාල population එකකින් එහෙම නැත්නම් finite population එකකින් ගත්තොත් එහෙම with replacement කතාව. right binomial එකට ගැලපෙන්නේ දැන් මෙතන තියෙන්නේ අපි ගත්තේ finite population එකකින් without replacement අවස්ථාවේදී සාමාන්‍ය. ඒතකොට ඒකටම ගැලපෙන විදිහට binomial එක කතා කරොත් එතන තියෙන්නේ finite population එකකින් with replacement අවස්ථාව. ඒ අවස්ථාවේදී කෙලින්ම x කියන්නේ binomial with replacement. right එතකොට මෙතනදී variance එක අඩු වෙන්නේ අතනදී variance එක වැඩි වෙන්නේ ඇයි? අතනදී හැම විස්තේම x ට ගන්න පුළුවන් බිඳුවේ සිට n දක්වා ඕනම අගයක්. හැම ට්‍රයිල් අපි මේ කියන්නේ නැවත නැවත එක්ස්පෙරිමන්ට්ස් දැන් මේ variance එක කියන්නේ මොකද්ද? අපි නැවත නැවත මේ එක්ස්පෙරිමන්ට් එක කරොත් එහෙම එක සැරයක් අරන් බලනවා කොච්චර x ප්‍රමාණයක් තියෙනවද? තව සැරයක් අරන් බලනවා කොච්චර x ප්‍රමාණයක් තියෙනවද? ඒකට ඒ විදිහට නැවත නැවත මේ එක්ස්පෙරිමන්ට් එක කරලා x ව නැවත නැවත ඔබ්සර්ව් කළොත් right ලැබෙන අගයන්ගේ variance population අගයන්ගේ variance එකනේ මේ variance of x කියලා කියන්නේ. right there is a population of x values that will be generated if we do this experiment again and again and again large number of times. Variance of x is actually the variance of that population of x values. එතකොට අපි අරක කරොත් එහෙම හැමතිස්සෙම x ට ගන්න පුළුවන් අගයන් තියෙන බිඳුව සිට n දක්වා. right මෙතනදී මේක මේ දැන් අර පළවෙනි එක ආපහු දාන්න නැතුව ගන්න නිසා x ට ගන්න පුළුවන් අගයන්ගේ සීමාවක් තියෙනවා. variability එක අඩු වෙනවා. right එතකොට ඒ අන්න ඒ නිසා තමයි මෙතන මේ variability එක අරකට සමාන වෙන්නේ නැතුව යම්කිසි correction factor එකක් ඇවිල්ලා තියෙන්නේ. ඒ correction factor එක එකට වඩා අඩු වෙන්නේ ඒ නිසා. මේක derive කරන්න පුළුවන් අපිට mathematically. නමුත් අපි ප්‍රායෝගිකව හිතලා බැලුවොත් ඇයි එහෙම වෙන්නේ කියලා ඒකයි ඒකට හේතුව. right set of values that can be taken for x has some restrictions. right here but in the previous case there is no restriction like that. So the variability is smaller here. right එතකොට මෙන්න මේවා තමයි වැදගත් දේවල් නිකන් අර සමීකරණ කටපාඩම් කිරීම නෙමෙයි වැදගත් අර තියෙන සම්බන්ධතා සහ මේ වගේ තියෙන අර වෙනස්කම් සහ සමානකම් තේරුම් ගැනීම. they are practically important. right right okay so you can see that Bernoulli and binomial and hypergeometric are kind of similar in a way that we all binomial and hypergeometric we are looking at the number of successes in a sample. right now we will okay මේකෙදිත් එතකොට මම මේ දීලා තියෙනවා r commands ටික I have given you the r commands මේකෙදි පොඩ්ඩක් මේ r function එක පොඩ්ඩක් අපිට ඕන විදිහට නෙමෙයි තියෙන්නේ ෆන්ක්ෂන් එක ලියපු එක්කෙනා ඒකේ ආගියුමන්ට්ස් දාලා තියෙන විදිය වෙනස්. එතකොට මේකේ සාමාන්‍යයෙන් අපේ අංකනේ අර binomial n theta කියෝ වගේ if x has a hypergeometric distribution we මේ අතර මෙතනදී universally accepted notation එකක් නැහැ. දැන් binomial එකේ නම් හැමෝම ලියන්නේ bin නැත්නම් binomial n first and theta second. එහෙම තමයි හැමෝම ලියන්නේ. නමුත් මේකෙදී තියෙන මේ notation එක universal නෑ මම එකක් තෝරගත්තේ. අපි කියමු hypergeometric m is the number of successes in the sample, k is the population size, n is the sample size. right එතකොට මේක බෙදුවම තමයි theta කියන එක එන්නේ අපිට. right ඒතර ওই විදිහට ගත්තොත් එහෙම මේ r වලට දාන්න වෙන්නේ අපිට ඒකේ තියෙන d hyper mass function එක ගන්න තියෙන function එක d hyper cumulative probabilities ගන්න තියෙන function එක p hyper. those are the two functions. එතකොට ඒකේට දැම්මොත් එහෙම ඒකේ තියෙන්නේ මෙතන තියෙන්නේ number of successes දෙවෙනි එක ඊට පස්සේ තියෙන number of failures ගන්න තුන්වෙනි ආගියුමන්ට් එක විදිහට තියෙන්නේ r function එකේ. ඒතර මෙතන හැටියට ගත්තොත් එහෙනම් මගේ notation එකට ගත්තොත් number of successes m නම් in the population so number of failures එන්න ඕනේ k minus m. right එතකොට ඒක මතක තියාගන්න apply කරනකොට ඒ arguments තියෙන විදිය d hyper function එකේ first එක x value එක simple x second value එක number of successes in the population this is number of failures in the population make a sample size. That's how the arguments are given in hypergeometric distribution. right අපි පස්සේ මුදා උදාහරණ ටිකකට දැනට ඔය ඇති කියලා මට හිතෙන්නේ. Shall we take a small break? Right, okay.